Okay, thank you for introduction. Thank you for the invitation. Really grateful, and I also enjoy this inspiring atmosphere here at the conference and of course at Mana. And yeah, it's a bit changing gears here. So it's about friction, and we use actually also quite a exotic way to measure that, as you will see. So we use sort of a force microscope where we attach some molecules, but you will see it's quite interesting, and I think that's also one of the nice thing about that topic, that friction, which you maybe think it's an old topic, more technological and so on, but it also enters now some really nice science. And of course I want to thank the collaborators here from the University of Basel, but also Shigeki Kawai here, who's here now at NIMS. Okay, so quick introduction to friction. So as I said, it's very old, so probably you remember Leonardo da Vinci already worked on that topic and found these famous fundamental laws. But there is still really some perspective, some technological need to improve the situation, and this is actually from Kenneth Holmberg, a recent article here in Tribology International, and he really tried to estimate what is possible nowadays, I mean, to reduce friction and basically save energy. And so it's quite interesting to see that about 1/3 of the fuel in a car is really used to overcome friction, so in the engine and of course also tires and so on. That doesn't include the energy loss due to braking actually, so it's really energy we can basically save if we improve the situation in the engine and so on. And there are now, he tried to estimate what is possible based on recent research results, and he found out that actually it looks like 18% could be saved by, for example, using oils with lower viscosity. That's probably something all of us already saw, that now they're using oils which have much lower viscosity than we had that some 10 years ago, and that tendency is going on. So this is something which is happening, and also within the next 10 years will continue. And but it also means we need much more demanding basically effects, because the oil has low viscosity. That means basically boundary lubrication becomes a problem. Anyhow, and then there are other concepts I will discuss here. It's also called superlubricity, so you can go really to very low friction values, as we will see, and that's probably on a time scale of more than 15, 20 years. Okay, that's sort of the introduction. Now, our instrument, well, it's not a Swiss Army knife, but it's actually the AFM, and the AFM really has this possibility. You can do imaging, of course. That's the most common thing you can do, and we saw already a lot of examples here at the conference. But of course you can do other things which are very valuable. So you can do local spectroscopy, you can learn about density of states, and I think for AFM especially we can learn something about the interaction. That's of course very what we will focus here. And then that's I think something which is really unique for this technique, is we really can do manipulation. We can move around molecules, atoms and so on, and you will see what you can do with that kind of possibilities. So the instrument I mostly focus at the moment is actually probably quite far from real application, because it's at low temperature and also ultra high vacuum. But I will try to explain you why that is quite meaningful. We also use this tuning fork here, which is a nice technique because it's relatively simple to use, and it can be combined with STM. It has a large spring constant, so this is around 1,800 Newton per meter. So this has quite some advantages, because you can avoid snap to contact and things like that, and also use small oscillation amplitudes. So normally you use dynamic modes. Okay, so as I told you, we will use it a bit in an unconventional way, this AFM. So here is basically the tip at the end, and you will see one of the first experiments we will do is really pick up here such a polymeric wire and basically pull it away from the surface. So the method to prepare this polymeric wire under vacuum conditions is of course not so trivial, because you cannot simply evaporate them. And so actually the most elegant way to really prepare very clean material which never saw really air or any humidity or any contamination is to evaporate a precursor, a monomer in that sense. That's this guy here. You evaporate it and afterwards you anneal it. Here in this case it was this dibromoterfluorine, so this basically these 3 units here, and you have this bromine at the end. So you evaporate on the surface, then you heat 200 to 200 degrees, and then the bromine will basically move away and it will form this polymer. So these little guys here, they are already these polymer wires. If you measure at 77 Kelvin, you see already they move a little bit. So there is some thermal motion going on. It also means they are not very strongly attached, or the diffusion wire relatively small. And if you measure at 4 Kelvin, they are basically stable. Okay, so now comes the experiment, which is done by Shigeki Kawai here. And you image first, and that's now really the special thing compared to previous experiments. For example, with DNA, things like that have been done, but normally there you don't know exactly what is the polymer. But here you can image now. You can count the number of units here. So we have 24 units. So these are these fluorine units. And now Shigeki approached here at this point here and formed a little bond to the tip, and then started to pull vertically away from the surface. And then you measure this signal, and this is what you see here. So you see really oscillation here, and if you now count this oscillation, you see actually there are 24 oscillations. And so this means it's the dominant effect here is actually the detachment of these units. So basically the subunits, basically each of them has to detach from the surface, and that gives you the strongest signal. There is also some substructure which is not noise here, but so if you zoom in into one of those peaks here, you can see there are little fine features here, and if you measure the distances here, you see that it's related to the substrate. So the substrate here is gold. You also see this herringbone reconstruction. So the wire actually moves in the valley of the herringbone reconstruction. And so it's not a peeling in that sense, but it's really also, you move upwards, but the wire also moves along the surface. And that motion gives you then some lateral forces or some frictional forces, which are relatively small and also not regular in this case, because the contact is not completely commensurate, but they can be related to this motion. So to understand a bit further, we also need some modeling here. So together with Alexis Bardov, we developed a very simple model for maybe some of you know the Frenkel-Kondorova model, which is one of the old models in friction, and this is in a way quite similar, with the difference that you basically pull on one end. So you have here springs and atoms in a way, and here you have the surface, and you see already that this is not commensurable, so we have not a completely regular pattern to expect. Okay, so what you see here, that's the experiment again, what we discussed before. You move away with the tip and you pull basically on this chain here, or wire, and here would be the modeling, and also it shows quite good agreement. So in principle, the main effect is really this detachment of the subunits. If you plot now the forces or the energy, you can see here the forces shows this oscillation because of this detachment around 0.1 to 0.2 nanonewtons. And in the energy, it's also quite clear. You have this stepwise increase of the potential energy. It's around 0.27 electron volts. So that's shown here again a bit more detailed. You can also see the elastic deformation and so on. This 0.27 electron volt, that's more or less the detachment of one of the subunits, and you can compare it with some, I mean, it's basically a methyl group which detaches from the gold surface, and that's quite consistent with some other expectation theoretical calculations. Okay, so that's the, let's say, the first experiment. There is an indication of friction, but mostly it's actually the detachment, so you can learn how much energy it really needs to detach this molecule. So now the second experiment is, you will see it's very closely related, but now, yeah, don't call that a molecule anymore, but you will see the method to produce it is very similar. It's a nanoribbon, a graphene nanoribbon, and we also basically attach it or pull it with the tip, and now you will see we also will move laterally, which is really then this kind of friction experiment. So the method to prepare it is really analogous to what we heard. So you start with a monomer, again with the bromine end groups, you heat it up, then bromine will diffuse away, and we have then the reaction here with forming first a linear polymer at around 200 C. If you further increase the temperature, you can form these nanoribbons, which, as you will see, turn out to be very nice and really only a few defects. So this is an example of an STM picture of such a ribbon. And now I show you how it looks in AFM. So I always call that sort of a Hubble effect. So you see that you really get a very improvement in the resolution, because the CO that's now attached to the tip, in that, for the imaging here, you can get closer to the surface, and now you really can see all the details of this ribbon. So it's basically free of defect. Only here at the end there is an additional hydrogen. Otherwise, of course, at the rim at the rim you have hydrogen also for the other parts. Okay, so now you can start experiments with that. So the first series here shows lateral manipulation. So this is a short wire, and you see you can move it around. This is a little bit longer, and you see also it's possible to move. Now 21 nanometer, you see it moves actually more or less also very easily. The forces are always around here a few piconewtons, so actually quite small, and they don't really scale with the length. So there is quite some variation, but you cannot tell that a longer wire would need much more. So this is a very long wire, so 55 nanometer. It also moves, and now if you plot the forces here, which were determined here by the method I will not discuss in detail, so you see there is some scatter. The main thing you can say is actually it doesn't depend so much on the length, but if you plot the force per length, then you see it really decreases. So you see immediately these are red points here. So clearly it's really not depending on the length. So it's somehow there is something there still which resists, but it's not depending how long it is. And so also if you take this, let's say 100 piconewton, you can estimate about the barriers which have to be overcome. So this is around 40 millielectron volt. So if you would do the same thing at room temperature, these ribbons would already diffuse around. So they are really relatively easy to move around, and that's also the reason why we call that already a sort of a superlubricity regime. Okay, so we can do further experiments. So you can really pick up again one of the ribbons, move up a little bit vertically and then horizontally. So you really, like a sled on the snow or something, you pull it along the surface. And then you can measure simultaneously the forces, and there you see some oscillatory behavior here. They're very weak again, so not very large forces, but they also show here this sort of a beating pattern. You see it sort of increases here in this area, and then has some minima here. And yeah, can do that a bit more systematic, so you can measure at different heights here, and you see there's quite typically you always see this kind of beating patterns here. If you go very far, I mean nearly before the whole chain or ribbon detaches, you also see multiple slips, but that's not so important at the moment. So this is now for comparison molecular dynamic simulation by Andrea Benassi and Daniele Bazzarone from EMPA. And so they really could reproduce, you see these beating patterns again, and they also reproduce basically this oscillatory behavior. And this can now be understood if we, because of course in MD you can see exactly where you are and which part or which location this ribbon is. And so it shows that if you are on the FCC area here, we get the minimums here, or if you are in the HCP areas also. But if you are in this transition regime between FCC and HCP, then we get the maxima. So it's somehow related to this commensability of the contact. So you can really now start to exactly see how the misfit of the ribbon relative to the substrate is. So it's in a way a sort of a surface science, but with something which is moving. So in that sense, of course, quite complex. But it's also here, this is a small one, which shows that shortly before the slip or before the movement of these little wires, you see that the biggest, or let's say the most attractive energy here, the largest forces are at the boundary or at the border here. So here's now a little movie moving in the ribbon moving in the -101 direction, and you see that actually along the ribbon there's not much structure to see, but at the end, so it's periodically repeated, so that's why it's entering on the lower side again. But now here you see it again, so basically the biggest effect is actually here at a detachment point here, and also at the end. So also you can see you can actually move it back. So that's also very special for graphene because it has this high modulus, or the Young's modulus of around terapascal. So you even can move it back and forward, and that works. And so this is a different direction. And here you see a bit more complicated pattern, a so-called Moiré pattern. So in this case, you see a bit larger frictional forces. It's still practically superlubric conditions, but still there is some remaining force because you have these little Moiré tiles which are not completely compensated. So the Moiré basically just means there are areas which the lattices fit better and areas where it doesn't, and one resists the motion and the other one not. And so we see that they're basically not. This is quite a complex pattern. Gives a bit more lateral forces, and actually experimentally we don't observe that motion. So actually the nature prefers the first case. So this is shown here again. The upper one is in the 1 - 2 direction. So this one gives a little bit larger one, and in the experiment we have this case where it's basically nearly no or a very weak Moiré pattern. And so we can say the special thing about nanoribbons is the high Young's modulus really allows that the lattice of the graphene stays more or less as it is, so it doesn't adapt to the substrate. So you can have basically nearly ideally this formation of this Moiré type of contacts, incommensurable contacts, and that gives you these superlubric conditions. So now the question, of course, can we use it, and also even for the real world, so to say, for the macroscopic world. And actually this is an example from the group from Ali Erdemir from Argon Lab, and they have used DLC, so diamond-like carbon, with diamond and graphene. And if you do experiment in dry environment, you actually can see really very low friction. So and actually for many cycles. So that means you can superlubricity in that sense is defined also by the friction coefficient, so just the ratio of lateral of friction force divided by normal load, and so this is 0.004. So if it's below 0.01, one usually calls it now superlubricity in this more technological application. So that seems to be promising, and what happens here is actually something quite special. So what one thinks is that this nano diamond, they basically roll up the graphene, and that thing basically is then used like something which can reduce the friction of the whole contact by supporting this slider. Okay, so I think I have not so much time left, but quickly wanted to show you something completely else, but also quite interesting topic, and it really shows a bit the strength of nowadays force microscopes. So this is van der Waals force between single atoms. So this is a xenon atom here and a xenon atom on the tip. So again, you use the tip as a probe. So you pick up an atom and you deposit the whole thing on a molecular network here. As we will see, it's a metallo-organic framework with these copper atoms here, and that stabilizes the whole this xenon, and then you can measure basically the interaction between single xenon atoms, the van der Waals interaction. So van der Waals, you know, it's typically this Lennard-Jones type of potentials here with power to the 6. If you also can sum it up, so it gives you really also long-range forces, for example, for the gecko to climb a wall, or for the layered materials, it's of course a quite important interaction to keep the material together. So, yeah, this is the whole setup. I mean, we go not too much in detail, so essentially you have first to grow this molecular network, a metallo-organic framework here, and then you put the xenon atoms here, and then finally you have the xenon on the tip and measure the interaction. So that's sort of the sequence. And just wanted to show you a bit, again, the flavor of STM compared with AFM. So this is the STM picture. So you see more or less, you just see where the molecules are. If you use a xenon tip, you can already sort of see what it probably is. If you use a CO tip, actually it's even better because you can get even a bit closer. So it's a bit more stable than the xenon, and then you can basically identify the different locations here of the molecule and really identify what you have. Also, what turned out to be important is that you use this focused ion beam modified tip to reduce the long-range forces. Now you can fill actually these nodes. There are two types of nodes. Maybe it's a bit of detail, but the main thing in the end is you basically measure once with a node filled with xenon and once without, and then you can take the difference, empty node versus xenon, and then you can also do it with krypton and argon, and actually you see that the largest is for xenon, the larger atom also, and then for krypton, and then for argon. And you can then calculate finally forces and also the potential energy. That you can basically now compare with typical pair potentials as we know them. And yeah, I mean, there were some surprises. I mean, for argon and for krypton is actually more or less what you would expect from the normal potentials we have available from gases and so on, the pair potentials. But for xenon, there is really a big difference. So this is the experiment here, and this line here, this other one, is the one we get from pair potential. So there seems to be quite some deviation. Even the R to the 6 doesn't follow very well for xenon. So xenon somehow already shows quite some deviations. And if you look a bit more detail, actually we see that the C6, so this coefficient from the power law, is actually quite different from the normal pair potential from gases. So we have here a factor of 2 to 4. So it also means that the polarizability of the atoms is really changed by being close to the surface. So yeah, okay, so I'm getting close to the end. I will not summarize now, but thank the group, and I just promised I will make a little advertisement here for our car nano race, nano car race. So there will be teams here from all over the world. I think especially, of course, also from NIMS there will be a team. There will be a team from France. So Christian Joachim will talk more about it. And we are also quite proud, of course, that we have a Swiss team, even though one has to say the driver here is a French and a German. So we are not too nationalistic, I would say. But so anyhow, you have to learn to drive a molecule around. So that's easy for us because we know the friction and so on. And so they can avoid the molecule here and drive it around. And here is a little movie showing that how they do. So they can really drive it here the way they want. So there are some regulations. Maybe Christian will tell more about it. And the funny thing about that topic, it's really fun for us a bit, is it attracts the media. We never saw that before. For example, this one is Red Bull magazine, and they made that's how they imagine our molecules. You see, it gets a bit science fiction now, but anyhow, that's the Swiss molecule, Swiss nanotraxtor, and that's the NIMS molecule here, and there are other ones. That's just to mention, and with that, I thank you for your attention.
Okay, thank you very much.